radar system is a highly integrated mechanism in which all components, of course, are essential. But the real heart of the system is the transmitter. The source of the energy for transmission is the oscillator. Now, the choice of an oscillator for any radar system depends largely on two factors. First, the operating wavelength, which is determined by the use for which the set is intended. Second, the peak power output which is required. All early radar systems operated at wavelengths of 50 centimeters or more. Many still do. But the trend is toward microwave operation, below 50 centimeters, which is used, for example, in these two sets. In order to obtain the ranges desired for most tactical purposes, the radar transmitter must emit radiations of rather high peak power, from 25 to 200 kilowatts, and in some cases up to 500 kilowatts. Such power cannot be generated in the usual triode oscillators. At 10 centimeters or less, the electron transit time is so small that the tube cannot be made large enough to deliver more than a fraction of the required power. The klystron, as we will see later, is used in conjunction with the magnetron as a low-power oscillator. It has the necessary frequency range and stability, which are the desired factors. Because it can produce a much larger peak power than the klystron, the magnetron is used as the microwave generator. A magnetron is really a diode tube so designed that the electric field which exists between its cathode and anodes will be perpendicular to the magnetic field which exists between the pole pieces of the supporting magnet. This combined electric and magnetic field is the key to the operation of the magnetron. In an electric field alone, the direction of the force exerted on an electron is opposite to the direction of the field. That is, electrons tend to move from low potential to high potential. In a magnetic field, the force of an electron is directed at right angles to both the velocity of the electron and the direction of the field. So the resulting trajectory is clockwise. When we combine an electric field and a magnetic field so that they are uniform and mutually perpendicular, we have two forces acting on the electron. The electric force upward, opposite to the direction of the field, and the magnetic force downward, or clockwise. As a result, an electron starting at any given point in free space and moving in this field will follow one of four types of orbits, depending on its initial horizontal velocity. The simplest path it can follow is a straight line. This happens only if the velocity of the electron is such that the electric force exactly equals the magnetic force. Hence, there is no deflection. Where the initial velocity is smaller, the electron starts curving upward at first. As it moves, it gains kinetic energy from the electric field, and its velocity increases. The magnetic force increases, and the trajectory is bent downward. The electron loses velocity and soon returns to its initial state. Then it repeats the orbit. An electron starting with zero velocity is acted on only by the electric field, and hence starts to move directly upward. As it gains velocity, the magnetic force increases, and its trajectory is bent over and down until it returns to zero velocity. The electric field acts on it again, and it starts up to repeat the same trajectory. An electron having negative velocity from right to left is pushed up by both the magnetic force and the electric field. It gains velocity rapidly. The magnetic force increased steadily, pushing the electron to the right and downward. The trajectory is bent back, and the electron is at its initial state. Then it repeats the trajectory. These four orbits, or cycloids as they are called, are typical of all which can occur in uniform and mutually perpendicular electric and magnetic fields. The horizontal distance covered by each electron in one cycle is the same, and the time required to complete the journey is the same. Now let's apply this knowledge to the operation of a magnetron. Consider a magnetron oscillator composed of a continuous plane cathode and an anode of several segments. Alternate sections of the anode are connected to opposite sides of the tank circuit. Now, if this is a CW magnetron oscillator, there will exist between the cathode and the anode a steady DC potential. Also, there will exist an RF field of the tank circuit. At the instant when the alternate anode segments are at their positive and negative values, the field of the tank circuit will look like this. The resultant of the combined fields will have this direction in region 1 and this direction in region 2. Since electrons tend to move in cycloids at right angles to the direction of the electric field, an electron leaving the cathode in region 1 would move like this. It would strike an RF electric field in its proper phase relationship and give up energy to the RF field. However, an electron leaving the cathode and entering region 2 will not be in the proper phase relationship to give up energy to the RF field and will quickly be returned to the cathode. The net result is that more energy is given to the RF field by the electron in region 1 than is taken away from the field by the electron in region 2. In this way, tube losses are overcome and oscillation can be maintained. The energy given up by the electrons to the RF field will change the polarity of those fields, so that at the end of one half cycle, the RF fields will be reversed. Thus, the electron, which has completed one half cycle in region 1, will now strike region 2 in the proper phase relationship to give energy to that RF field. This process will continue until the electron eventually reaches the anode. All electrons which move from the cathode to the anode will follow this course. Of course, in a pulsed magnetron oscillator, where the electric field does not exist between pulses, the electrons will be affected only by the magnetic field, and so will be returned to the cathode. Now let's look at a typical magnetron. Imagine the 6 anode segments of the plane magnetron arranged in a circle around the cathode. The distributed inductance and the interelectrode capacitance form the necessary tank circuit for oscillation in the microwave region. For this reason, magnetrons usually are designed to operate at only one frequency. However, because of the coupling effect between anode segments, 3 frequencies can be excited, each with different RF fields set up. This is one possible frequency with its resultant electric field. This is another frequency with its resultant field. And this is the most efficient frequency with its resultant field. It is this frequency at which the tube is designed to operate. It will do so if the proper magnetic force and the correct DC potential are applied. With the magnetron oscillating at this frequency, electrons leaving the cathode are governed by the same forces as those in the plane magnetron. The electrons leaving the cathode will move in the usual cycloids, passing 2 segments per cycle of the oscillator until they finally reach the anode. By using a segmented anode, the electrons are made to work against an alternating electric field crosswise to the steady field. In this mode, the RF field gives the electron a finite transit time, which is 2 anode segments per cycle. But no definite time is set for the electrons to move from the cathode to the anode. It is this fact which makes it possible to build a magnetron large enough to deliver sufficient peak power to operate a radar system in the microwave region. In actual practice, large numbers of electrons will leave the cathode at the same instant. Those entering the RF field out of phase, of course, will be returned immediately to the cathode. But those entering in phase will follow the usual orbits until they strike the anode. Thus, there will be bunches or clouds of electrons in the in-phase region and very few in the out-of-phase region. And the clouds will revolve in the same direction as the individual electrons, always approaching an RF negative segment of the anode. In this way, the kinetic energy, which the electrons obtain from the DC potential, is given up to the RF field, and oscillations are sustained. We have seen how the pulse to be transmitted is generated. Now we will examine the second function of the radar set. The transmitted pulse must also be received and displayed. However, the signal which appears on the cathode ray tube must be at a video frequency which is much lower than the transmitted pulse. To produce this video frequency is one of the main functions of the radar receiver. This receiver uses the superheterodyne principle. By mixing the incoming signal with a local signal in a crystal or tube mixer, an intermediate frequency is produced. The intermediate frequency component, which is separated in the detector, is amplified in the video amplifier and displayed on the cathode ray tube. The generation of the local signal, which is mixed with the incoming signal, is the function of the local oscillator. Since the intermediate frequency is only a fraction of the incoming frequency, the local oscillator must operate at almost the same frequency as the transmitter. For instance, at 10 centimeters, or 3,000 megacycles per second, where the IF is usually 30 megacycles per second, the local oscillator must operate at 2970 megacycles per second. And it must have very great frequency stability, since the IF amplifier is designed to pass only the one frequency. For use as an oscillator in the microwave region, reflex velocity modulated tubes have been developed. There are several types: the Sperry-Klystron, the McNally, and the Shepard-Pierce. The tubes in relation to a magnetron are comparatively small, since the peak power requirements for a local oscillator are not great. While these velocity-modulated tubes may vary somewhat in their construction, they all operate on the same basic principle. They all employ cavities as the resonant element with collecting grids between and connected to a B-plus source. This determines the frequency and places an alternating voltage between the two grids in the tube. An indirectly heated cathode is the source of electrons. They are attracted to the cavities by a large positive potential on the cavity grids. To speed them up still more, there is an accelerator grid connected to the B-plus source. After the electrons pass through the cavity grids, they encounter a strong retarding field produced between the cavities and an electrode known as the repeller or reflector, which is maintained at a still lower potential than the cathode. This, then, is the tube. If we assume that the tube is in oscillation, this is what happens. The electrons leave the cathode, are speeded up by the accelerator grid, and presently arrive at the cavity or buncher grids. Across these grids is the high-frequency alternating voltage of the resonant cavity. Since the electrons pass between the buncher grids in a shorter time compared to the period of oscillation, their velocity is altered by the change in potential which they encounter. The electrons passing upward when the RF field between the grids is in a positive direction will be accelerated. Hence, they will move almost to the repeller before being turned back. Electrons passing through when the RF field is in a negative direction will be decelerated, so they will go on only a short distance toward the repeller. The point at which an electron is turned back depends on its own velocity as it leaves the buncher grids and the voltage on the repeller. Now let's take 3 electrons as they leave the cathode at slight intervals and see how the bunching effect is produced. The first electron leaves the cathode and reaches the buncher grids at a time when the bunching voltage is maximum accelerating. It is speeded up so that it goes almost to the repeller before being turned back. The second electron, leaving the cathode an instant later, reaches the buncher grids when the bunching voltage is 0. Its velocity is unchanged, so it is stopped before approaching so close to the repeller. The third electron, leaving the cathode still later, reaches the buncher grids when the bunching voltage is maximum decelerating, so it goes only a short distance toward the repeller before being turned back. Since the first and second electrons will have to travel farther than the third to return to the buncher grids, the net result is that they will all return at approximately the same time. This is what is known as bunching. One bunch is produced for each oscillation of the cavity. If this bunch returns when the voltage across the buncher grids is such that it slows them down, they will give up energy to the alternating field. If the voltage is maximum decelerating, They will give up the maximum energy, and the oscillator will produce the maximum output. The output is taken from the cavity through a coupling loop. Of course, in actual operation, large numbers of electrons leave the cathode and move toward the repeller plate as an electron beam. As they pass through the buncher grids and approach the repeller, they become bunched. And the repeller is so spaced, and the voltage applied to it is such that the bunches return to the buncher grids in the proper phase to give up energy to the RF field. Spent electrons return to the B+ source, either through the grids of the resonator or through the accelerator grid. It is by bunching, then, that kinetic energy supplied by the accelerating voltage is subtracted from the electrons and used to sustain the oscillations in the cavity. For maximum output, a reflex velocity modulated tube must operate at the resonant frequency of the cavity. However, the operating frequency can be varied slightly by changing the negative potential of the repeller so as to alter the bunching action. If greater changes are necessary, the volume of the cavity must be altered, or the cavity grid spacing must be changed by an outside mechanical device. The advantages of the reflex velocity modulated tube become apparent. By using cavities as the resonant elements of the circuit, we get great frequency stability as well as the required power. By modulating the velocity of the electrons, the transit time from cathode to anode becomes a working factor in the operation of the tube rather than a limiting factor, as in an ordinary vacuum tube at high frequencies. The development of the magnetron made it possible to radiate a powerful signal at 3,000 megacycles and above. The development of the reflex velocity modulated tube made it possible for the signal to be received and displayed. Radar can now operate efficiently in the microwave region.